Now, if we spend just a minute in reflecting, intuition tells us that this decimation needs to be outdone when we reconstruct in some manner. What do we mean by outdoing or doing away with that decimation? You see, what has happened as a consequence of that decimation process? In some sense, that decimation process has halved the n index. So, recall that decimation process essentially brought the index 2 to the index 1, the index 4 to the index 2, the index minus 2 to the index minus 1, and so on and so forth. We need to restore the indices back to their original place, that is at double the value. So, how do we do that? So, essentially, if we wish to construct a synthesis filter bank or to synthesize y t from y v 0 t and y w 0 t, actually in time it is very easy, in continuous time it is very easy. In continuous time, this is simply y t is y v 0 t plus y w 0 t, simple. So simple, you just add them, but that is in continuous time. When you want to do it in discrete time, you have to work a little harder. So, in fact, let me put back the sequences. Let us write the sequences explicitly now. What we will do is we will write down the sequences, at least in that region from minus 1 to plus 3, explicitly for y v 0 and for y w 0. So, let us write the sequences explicitly. So, for y the sequence is essentially 10, 16, 14, 11, 3 minus 1 here and 7 4 there and 0 marked here. Let us on the same reference write the sequence for y v 0 and y w 0, and then let us put them together. What I will do is when I write the sequence for y v 0, I will need to do a little bit of work. Y v 0 is going to look like this. So, in fact, I have the sequence here. Let me just rewrite it explicitly. So, I had the sequence for y w 0 here, I put it down explicitly. Now, you see what I mean. You see, if you look at this sequence, it has in the interval from minus 1 to 3, 2 plus 2 plus 2 plus 2, 8 values. And if you look at these two, they have only 4. So, somewhere we have to do an expansion, and that expansion is required because each of those points in the sequence corresponding to y was actually over half an interval, half a unit interval, whereas the sequence points in yv0 and yw0 are on a full unit interval. So, essentially what we need to do is to introduce spurious zeros here. So, let us first carry out what is called a process of interpolation or upsampling. So, now let us define with the intent of outdoing the operator of decimation to outdo decimation, so to speak, to outdo or overcome decimation. Let us define an operator which we shall denote by up and to. Up essentially means upsample. And what does up and to do? Well, up and to essentially introduces a 0 between successive samples. So, if you have x in as a function of n, and you subject this to the action of up and to produce x out as a function of n, then x out of n shall be equal to x in at n by 2 for n a multiple of 2. And 0 else. When n is not divisible by 2 or not a multiple of 2. So, let us illustrate this operator. For example, suppose x in of n happens to be the following sequence. Let us take the very sequence that we have for yv0. So, I have yv0 n. So, you have 13, 25 by 2, 1 and 11 by 2 marked with 0. What will x out n look like after upsampling by a factor of 2? Firstly, it will have 8 locations. So, it will be 11 by 2, then 0, 13 and then 0, 25 by 2 and 0 and 1 and 0, and 13 would of course come back to 0. So, this is how the up to sequence looks for the sequence yv0. Similarly, we can construct yw0 n upsampled by a factor of 2. Let us write that down explicitly. So, if we take yw0 n and upsample it by 2 in the way we have done for yv0, we get the following: minus 3 by 2, 0, minus 3, 0, 3 by 2, 0 and 1, 0. And 3 of course is located at 0. So, now we are in good shape. You see, what we now need to do, if we think about it, you see, you want to reconstruct y of n from these two. And for example, let us look at these two upsample sequences. So, this is the upsample sequence corresponding to V0, and this is the upsample sequence corresponding to W0. Now, how would we get the piecewise constant values from these two sequences? Well, let us take the example of the first two values here. The first value in the upsampled sequence of V0 is 11 by 2. So, 11 by 2 and 0, and minus 3 by 2 and 0. So, if we simply added them, you can see that if we simply added them, let me put them together for reference. So, I will just suppress this for the moment and let me just put them together, just these two sequences. So, in these two half intervals, now remember these actually correspond to half intervals here. 11 by 2 minus 3 by 2. In other words, when you add these, that is 8 by 2 would give you the value of y t between minus 1 and half, 4. And 11 by 2 minus of minus 3 by 2. In other words, 14 by 2 would give you the value of y t in the interval from minus half to 0. So, what you need to do? You need to operate the sum filter, this plus this, for the first half interval and this minus this for the second half interval. Let me write this down explicitly. So, you see it is interesting what we are doing here. You must understand what is slightly different between the analysis and the synthesis filter banks. In the synthesis filter bank, it is as if one filter operates for one sample and the other filter operates for the next sample. And therefore, you could visualize a situation where you carry out both the filtering operations at once, but then allow this sample or the sample from the upper filter to pass in one instance and the sample from the lower filter to pass in the next instance and keep alternating in this way. How do we express this in the language of discrete time signal processing in the Z domain? Well, let us draw the diagram first. So, what we are saying is this: I have this sequence corresponding to V 0. So, y V 0 n, and I have the sequence corresponding to W 0, y W 0 n. I have upsampled them. Now, I also subject this I subject to the filter 1 plus Z inverse. Remember, this is the filter where the output B n and the input A n are related according to B n is A n plus A n minus 1. And here I subject this to the action of the filter 1 minus Z inverse. All right. Well, I think it might be easier for us. So, what we want to do, I think maybe it will be a little difficult to see this directly. Let me instead put it down as an operation of addition and subtraction directly. Let me make a little change in this. Let me say instead I have y V 0 n and y W 0 n here. I upsample them and I add and subtract. So, now I get the outputs of upsampling. Now, I add and subtract. So, I have the sum of these outputs on one branch, this plus this, and this minus this on another. This is the sum branch, this is the difference branch. And what I am saying is, I pass the sum branch at one instance and I pass the difference branch on the next instance. And remember, this is operating at twice the rate. So this upsampling operator needs to be located slightly differently. We have to interpret this properly. We are saying essentially take the sum branch at the 2nth point and the difference branch at the 2n plus 1th point. So, let us write that down. Let us call this the point 1 and the point 2. Alternately take one and 2. Now, how do we express this using the upsampling operator that we have? Well, that is easy. Actually, if we notice, this upsampling operator can commute with this. So, it does not matter if you first upsample and then add and subtract, or if you first add and subtract and then upsample. In fact, we would find it convenient to add and subtract and then upsample. So, let us replace this. Let us redraw this. So, we have a sum and difference branch here. Recall, this is what we call a signal flow graph. In a signal flow graph, we have nodes and we have edges. A signal flow graph is a convenient way of showing computation. You will recall that whenever you have a node at which you have multiple edges coming together, the content of the edges is added together. It is as if each edge starts from its source node and goes to its destination node, multiplying what it carries from the source node by the multiplier on the edge and deposits it at the destination node. So, the destination node, any node which has edges coming into it, is equal to the sum of all the deposits coming from the edges. And if many edges go out from a given node, all of them carry the value of that node with them multiplied by the multiplier on the edge. Just a recapitulation of the signal flow graph notation. But coming back to this signal flow graph that we have drawn here, I have essentially these two nodes where two edges come in appropriately with multipliers. These are all multipliers of 1 and this one of minus 1. And now I put an upsampler of 2 here for convenience. And indeed, what I want to do is to pass this as it is for the even instances, but this I wish to pass for the odd instances. So, how do I express that process of passing for the odd instances? I express that by delaying this by one sample on the upsample rate. So, here I need to put a delay operator in the z domain, which is z to the power minus 1. What does this z to the power minus 1 do? It shifts this by one step forward. So, if you notice, at the 2nth point it is this which will come, and this would come not at the 2nth point, but at the next point, the 2n plus 1th point. And then you would have this together giving you the sequence that you desire, the sequence corresponding to y, which is yn. So, this is the synthesis . The synthesis process or the synthesis filter bank. It is interesting. If you notice, in the analysis filter bank, we put down the filters explicitly and then had a downsampling operation. Here we seem to have the filters implicitly. So, you have a combination operation being done first, essentially an add subtract kind of operation, followed by an upsampler and then followed by some operation in the z domain. So, in fact, what we have done without realizing it is also brought out an efficient way of implementing the synthesis structure. I told you somewhere earlier in this course that the Haar multi-resolution analysis and its derivatives, that is the filter bank coming out of the Haar and the other concepts that are illustrated from the Haar, illustrates several different ideas, several different common concepts in multi-resolution analysis very, very lucidly, and this is one example. Here I have a beautiful decomposition of the synthesis filter bank into what is called its polyphase components lying ready for me right here. Now, this word polyphase we will illustrate in greater detail later. What I am trying to say is that the structure that we have drawn right here for the synthesis filter bank actually gives us an efficient way of computing or representing the computation of the synthesis filter bank. And if we will only take a minute to understand that this upsampling operation can jump back and forth, can jump back and forth here. So, here when we drew this diagram, we were not quite correct. This is intuitively okay, but this needs to be corrected, needs correction. In fact, now we have the corrected version emerging from here, and let us draw that corrected version by placing the upsamplers back here. Remember, the upsamplers commuted with this operation here. So, if we do that, we have the following structure. Y v 0 n, y w 0 n, upsample by 2, follow it with a sum difference operator, but remember there is a Z inverse there. And this is what is added. So, you see, if you like, you can bring the addition here, it does not matter. So, look at what is happening. What is the operator acting on y v 0? What is the operator acting on this branch? This branch comes here with a transmissal of 1 like this and a transmissal of Z inverse like this, and this branch comes here with a transmissal of 1 like this and a transmissal of minus Z inverse like this. So, in other words, what we have is the following structure, with which we shall then conclude today's lecture and look more deeply in the next. The structure that we have is this. We have an upsampler, we have a 1 plus Z inverse operator coming there, and a minus Z inverse plus 1 operator coming here. And these are being added to produce y n. We shall delve further into this structure in the next lecture. But what we have just done a minute ago is to construct a synthesis filter bank for the Haar multi-resolution analysis. We shall build this further in the lecture to follow. Thank you.
Hello everyone, I am Nikunj Patel. You can ask any questions or doubts if you have regarding the material covered in the class.
Hi Nikunj. In the equivalence relationship between functions and sequences, can you elaborate on the constant term that appears in the inner product of sequences?
Yeah, we can derive that constant term analytically using the fact that the basis functions for the sequences are orthonormal. We want to derive the value of kh0 that exists in the equivalence relation between inner product of function and sequences. K0 generally depends on the space Vm in which Ft and Gt belongs. Ft is equal to sigma Fn phi 2 raised to m t minus n. Gt is equal to sigma Gn phi 2 raised to m t minus n. The product between Ft and Gt is equal to integral of Ft G conjugate T dt. But here we are assuming Ft and Gt are real sequences, hence complex conjugate will be same as Gt. So it is equal to Ft Gt dt. We will try to substitute Ft and Gt in terms of the basis functions. L is some dummy variable phi 2 raised to m t minus L, and sigma p gp phi 2 raised to m t minus p dt. We will take Gp and Fl common, and it results in double summation Fl Gp, and the results in integral we know that phi is an orthonormal basis for Vm, and this is equal to 2 raised to minus m if and only if L is equal to P, 0 else. Hence this double summation results into single summation 2 raised to minus m Fl Gl. Hence we proved that inner product of Ft Gt is equal to 2 raised to minus m times sigma. We will replace this dummy variable L with n. This is the value of k0 that we want to find out. k0 is equal to 2 power minus m if Ft and Gt both belongs to Vm.
I had a query that in the hard filter bank, why do we analyze before only to synthesize later?
It generally depends on the application. After analyzing the signal using wavelet, we are modifying the signal and then we are synthesizing. Means it depends whether we are doing denoising, compression or any other application. So some applications we are first analyzing, processing the coefficients, and then we are synthesizing the signal back so that we get the desired signal. For certain applications, we want to decompose the signal in, for example, image processing. We want to decompose the signal into its wavelet coefficient modify it depending on application and synthesize the modified coefficients. For example, consider two-band filter bank. We can further analyze this block depending on the application. And for example, if we apply this filter bank to the two-dimensional signal such as image, then we'll apply this filter HN to the image row wise and then column wise. For example, if we apply first HN row wise, downsample it and then apply HN again column wise, downsample it, then we will get the low band of image. L for low pass, because we are applying HN, which is a low pass analysis filter, twice. If we apply low pass filter HN row wise, downsample it and then apply high pass filter GN column wise, then we will get LH band. We will repeat this for high pass filter row wise and low pass filter column wise, then we will get HL. And if we apply high pass filter both row wise and column wise, then we will get HH band. We can further decompose this LL band into its subbands. What is the importance of this? For example, if you have a low resolution phone and your phone can't display high resolution images, then in communications we are transmitting only the LL band of an image. It will be sufficient for a phone, for a low resolution phone, to display this image using less number of bits. But if you have high resolution phone, then we are sending the whole image as such, and if you want to reconstruct the high resolution image, then you can add this detail components into the image and reconstruct it. If you want to see a low resolution, then you can see this LL band. It will look like an image, but the details are missing in this. It's somewhat a blurred version of image. This has very good application in web. For example, in 1990 you have seen that the image in a phone comes from top to bottom. It is coming like this, and then at the end you are going to see the whole image. But nowadays you see that on Facebook or WhatsApp they are showing you a blurred version of image. Means first the LL band is transmitted and then this LH band is transmitted first. So if you receive the LL band first, then you will get the blurred version. Blurred version is displayed first, and after receiving this detail band, they will add the detail band to the image and you will get the full detailed high resolution image. Thank you.